This is the two-problem piecewise function review for getting a couple points on your piecewise problem set. These are a little more complicated than the ones that were on the yellow sheet, so that should be good. I'm gonna, if you want to, you might want to pause it and write this problem down, and then also, you can just draw a little graph below it too. You probably don't have graph paper available. I'm actually going to add another third part to this piecewise function, and I'm going to say, I'm going to add it at the end just so I'm sure what I want to do. So with these piecewise functions, what I would suggest you do is go look at these boundaries. They tell you what chunks of the graph you're going to be splitting up. And I usually, you don't have to, but I like to put like what I would call a fence or a barrier. It's not an asymptote. So I kind of do it dotted. And at 0, I've got a boundary. And at 1, 2, 3, 4, I've got a boundary. So I'm going to just do this in blue. And then over at 9, I've got a boundary. And this first piece right here is going to be in this portion of the graph. So this first function is going to live kind of right here between these two fences. Because of this equality here, I actually get to be on both fences because it says greater than or equal to 0 and less than or equal to 4. This function right here is going to live between the 4 and the 9. It can't be on the 4 fence, but it can be on the 9 fence. So I would kind of structure it like that. Then what I'd also suggest you do is kind of go have a good understanding of what these functions look like. You should look at this one right here and go, okay, that's going to be a line. It's downhill because it's got a slope of -1/2. So between those first two fences, I'm going to have a line going downhill. This right here is the absolute value parent function. So I'm going to have a v of some sort. Remember, when f of x is equal to the absolute value of x, we get this nice v centered at 0, 0, 1, 1, -1, 1. But I've subtracted 6 from it, so it's going to be going 6 to the right. And up 10, also this negative means it's going to be flipped over. So in that portion of the graph, I'm going to have an upside down v with its vertex at 610. It just really helps to have a visual. I haven't even really graphed anything yet, but I'm going to right now. So the first one, I always suggest, I'm going to erase all this organizational stuff I wrote for you. So now to get started, what I would suggest you do is see what happens on the fence. So put a 0 in here, and you get a 6. So go to 0, 1, 2, 3, 4, 5, 6, and again you get to live on that one because it says greater than or equal to. Then go put a 4 in here, and you'd have -1/2 of 4 plus 6, which would be -2 plus 6, or the point 4, 4. So on this fence, 1, 2, 3, 4, 1, 2, 3, 4, I also get to have a solid line here. Now keep in mind it was supposed to have a slope of -1/2, and if I go down 1 over 2, down 1 over 2, I do have that nice, so if you just see what happens on the fences, if it's a line, just connect them. That's the easiest thing to do. So I've now taken care of the first piece of the graph. You might say, well, what's happening over here? Well, I haven't defined it over there. I don't have what happens when I'm less than 0, so I don't graph anything over there. All right, so my next one is that absolute value. And again, I'm going to see what happens on the fence. So I'm going to put a 4 in here. I'm going to have my 4 minus 6, my -2. I need to take the absolute value of it, which is 2, and then take a negative and add 10 to it. So when I put a 4 in there, I'm going to get an 8 out. So I go to 4, 8, and I put an open dot because it says I have to stay greater than 4. Now that means I can be 4.011000001. So I can get right up to the fence. I just can't be on it. Then plug the other point in. And again on that one, you would have 9 minus 6 takes its absolute value, which is 3, and you do -3 plus 10, which is 7. So it looks like at 9, I'm going to be graphing 9, 7, which is right here. And I'm going to be living right on it. Now what happens in between? That's pretty important. The key thing when you graph a parabola or the absolute value function is to know where that vertex is. And we already talked about, on the parent function it's at 0, 0, but this moves me 6 to the right and 10 up. So I'm going to peak out up at 6, 10. So I'm going to go put that on my graph, because otherwise, you know, with a line you just connect them. But if you're looking for that curve or that V, you really do need to know where that vertex is. So I'm going to go to 6, 10. And now I'm really clear that this is my graph. And that one's done. But I'm going to add a third piece to this, just because it was on your yellow sheet and a couple of you got kind of goofed up with it. I'm going to define f of x as equal to 7 when x is greater than 9. And what that means is, you know, if you think of f of x as being y, I've got my y equals 7 everywhere I'm bigger than 9. I go to 9 and I technically put an open dot, but it's already defined there and it's already closed. So everywhere greater than 9, I'm going to have a y value of 7, which will go this way. And then I had that continuity question on here. This function as a whole is not continuous, because if I started over here on my very first fence on the left, if I drew that, I'd have to lift my pencil to go up here and draw that. So as a whole, this function is discontinuous. However, if I had asked you from here to here, then it'd be continuous because I don't have to lift my pencil on that portion. But your job was for the whole entire piecewise function. So as a whole, that is discontinuous. The next one is two parts again. And again, you should look at that and go, okay, I got a line, I got a parabola. And then go plug in, we'll go faster on this one. Go see what happens on those fences. Well, I'm going to go draw them on here very lightly. I can get right up to -2 and live on that fence. I can get right up to 1 and live on that fence. So between these two fences, I'm going to have this line. Well, let's go plug it in. I've got -2 when I plug in there. We'll spit out 4 minus 1 is 3. So I'm at -2, 3 on that fence, and I get to live on it because it says equal to. Then I'm going to go put in a 1. And I get -2 minus 1 for a -3. And again, I get to live on the fence there. So I'm going to just connect those. And you can see I've got that y-intercept of -1 right here, which is really good. I'm going to take that dot off there right now. And it looks good. There's my piece of the graph between -2 and 1. And it's solid dots because I can be on them. Now this says everywhere to the right of 1, which is in this piece of the graph. I need to graph this function. Well, let's see what happens at 1. Because again, although it says greater, I can be 1.000000, so I have to get right up to that fence. I just can't be on it. So I'm going to go see what happens when I plug in a 1 right here. I would have -1 minus 3 squared plus 5. So I'd have a -2 squared plus 5. So I'd have a -4 plus 5. I'd have a 1. So when I put in a 1, I got a 1 out. So at 1, 1, I'm going to go here to this fence, but I'm going to leave it open. Technically, I haven't graphed anything yet, but it gets me, my graph needs to get right up to that dot. So now the problem is well, I know it's a parabola, but where does it go? And that's again where you need to, for a line, you can just connect them because lines are straight. But when you've got a curve here, I've got to know where to take that curve. Do I take it, you know, swoop down, or do I swoop up? What do I do? And so I'm going to erase this. You need that vertex. Well, on the parent function, the vertex is 0, 0. And again, this is going to slide me 3 to the right. This is going to slide me 5 up, and the negative is going to flip the parabola over. So my vertex is at 3, 5. I'm going to go put that on there. 1, 2, 3, 1, 2, 3, 4, 5, right here. So I know I'm going to come up and then down. And again, you can just go like that if you want. It doesn't have to be perfect. So again, I've got another discontinuous graph because I've got, when I draw it, I've got to lift up my pencil to complete the rest of it. So this would be called discontinuous also. Again, and if I threw another portion on here, maybe, I think we're good. I'm going to be done with it. Bring that to me.